Hello and welcome to GarageAuto's final design presentation. Here are the team members that make up GarageAuto. My name is Andrew Corielli and I was the project lead of the group, and I was also in charge of the physical design of the product.
Hello, my name is Connor Roche, and I assisted with the physical design and was the lead documenter.
Hello, my name is John Schwartman. I was a lead software developer and I assisted with app and physical design.
GarageAuto was created in order to make the garage door opening process automated instead of automatic. By using an app, we are reducing the number of personal items that are carried in the car. Anyways, apps are for everything, even opening the garage. Shown below is a comparison table of how our product stands up to others. We pride ourselves on our price and simplicity, and that is where we shine versus the other products.
The block diagram for the GarageAuto system can be seen here. Starting from the bottom left, we have the power supply. This supply takes in an AC input and outputs a 5-volt DC and a 3.3-volt DC output to power the relay and microcontroller respectively. Next, the microcontroller block. This depicts the components that are directly connected to the microcontroller. This includes the microcontroller systems, the Bluetooth transceiver, the onboard LED, and the onboard reset button. Finally, the last three blocks are divided into two groups. The transistor amplifier and the relay allow the interaction between the central control system and the existing garage door opener, while the app block allows interaction between the user and the central control device.
So how does this all come together? Well, on the app side of operations, we have a few certain key functions. Upon initial use of the app, the user must go through a first-time setup stage. This setup will allow the user to verify they're a valid user via a password. Also, inside the setup, the user can record the home position for where the garage door is located. This set home position will be crucial for distance ranging operations. If this is not the first time the software is used, then the user can either proceed to main operations or choose to change the previous stated settings parameters. Now that the setup is initialized, the main operations of the software can commence. First, a geofencing decision is made. Geofencing works in conjunction with GPS and is where a perimeter is set up around a location. At the boundaries of this perimeter, events may trigger whether the fenced-in area has been entered or exited. For our solution, we will be interested in when the geofence region has been entered. Upon entry of this region, the app will be triggered to wake up from background mode and begin scanning for the Bluetooth device, the garage door opener, to begin pairing. Also, upon entry, a momentary software switch will be flipped on. This will allow for non-concurrent device triggers and will only allow the garage door to open once, upon arrival. Once this pairing process is complete, only then can data be sent to the garage door opener. After a set amount of time, the app will return to the background to conserve the phone's resources. This main process will repeat after the geofence region has been exited and will resume when the region has been re-entered. Now, what happens on the other side of the garage door? On the microcontroller side of the software is where we can actually open the garage door. Upon boot up, the microcontroller sets up and initializes the hardware for use. Once the hardware is set up and the Bluetooth radio is ready for use, then the microcontroller can begin to advertise it is ready to connect. The app will establish connection to the Bluetooth and begin sending data. The data that is received will consist of a few different formats. The key data sets used are user data, a settings parameter, and location data, as well as the momentary logic. The momentary logic is the same as mentioned before and allow the garage door to only open once upon arrival. The user data will be used as a verification metric and will be judged to determine if the data received is from a valid source or not. If the settings parameter is received, then the microcontroller will proceed to wait for the preceding location data. That location is then stored as the home location to be used later. If the settings are not being mutated and the data receives from a valid user, and we are receiving location data, then we can proceed to determining a distance. This distance calculated is the current distance that the user is from the garage door opener. If the distance is less than the set parameter and the momentary logic is set to true, then and only then can we open the garage door. This process will repeat as long as there's still incoming data being received from the app. If at any point the connection to the Bluetooth is lost, the microcontroller will return to an advertising state and wait for connection to be reestablished.
When it came to picking components for our project, we decided that the PSOC 6 was the best microcontroller we could go with because it was a multi-tool of a microcontroller. It had a Bluetooth transceiver and receiver, and it could also output a little bit of current from the GPIO pins. We realized later on in the semester that we needed to amplify this current quite a bit in order to hit the 2 amp switching current of the relay. So we used the TN7000 to amplify the current we were outputting to match that 2 amps. Once we did that, everything worked ideally. The other component we needed was the voltage regulator, which dropped the wall adapter voltage from 5 volts down to 3.3 volts to safely power the microcontroller.
The following are the major technical specifications for the GarageAuto system. Starting from the top, we have the power supply input voltage. This has a minimum of 100 volts and a maximum of 240 volts. These values come from the reported voltage range of domestic electrical outlets in North America. Next is the power supply input current. This has a minimum of 0.2 amps and a maximum of 0.3 amps. These values were obtained in the same way as the input voltage. Then we have the power supply output voltage. This has a minimum of 5 volts and a maximum of 5.5 volts. These values were given by the parts datasheet. Next is the microcontroller operating voltage. This is the voltage needed to effectively power the microcontroller. The minimum for this is 1.7 volts and the maximum is 3.6 volts. Like the output voltage, these values were acquired from the relevant datasheet. Next, we have the effective operating temperatures. This has a range of -40 degrees Celsius to 80 degrees Celsius. These values were acquired by finding the largest minimum and smallest maximum temperatures from all relevant part datasheets. For example, the relay we used is rated for a maximum temperature of 85 degrees Celsius, but the power supply is only rated for 80 degrees Celsius. So the 80 degrees Celsius maximum was chosen as the supply could break if we used the relay's maximum. Finally is the effective operational humidity. This has a range of 5% humidity to 85% humidity. These values were acquired in the same way as the temperatures, taking the largest minimum and smallest maximum of all relevant parts.
Now these are the software specifications that we've decided to use. The first one will be using Bluetooth as communication standard. We decided to go with Bluetooth 4.1 or greater. Using Bluetooth 4.1, we are able to use Bluetooth low energy. It will allow for greater theoretical ranges so we can connect to it, and it will also allow for greater data throughput, which will be beneficial for future expandability. Next, we have location services. For location services, we will be using GPS, or Global Positioning System. Using GPS will allow for offline positioning acquisition. Our system will be mainly used and outdoors to allow for maximum accuracy. With GPS, we'll have a tolerance of plus or minus 5 meters with sufficient number of satellites acquired. GPS will be required for certain software features such as geofencing. For majority of the software we use, we adapt into a mobile operating system. The mobile operating system we were using will be used for Apple iPhones with iOS 12.0 or greater. Using iOS 12.0 or greater will allow us to use the background Bluetooth functionality. It will also allow us to use a geofencing feature, and using iOS 12.0 will allow us for compatibility with older devices. And last but not least, we have Bluetooth connectivity range. We decided to go with 0 to 60 feet for a minimum range. We decided this because this is the typical distance a car would be located when parked in front of a garage to the garage door opener. Environmental factors may limit this range performance, which will be further explored later in testing.
Here's how we tested GarageAuto. The main metric we tested for was the connection range for the Bluetooth. This is because the two major metrics involved with the functioning system were not distance sensitive, in the case of the geofence, or had virtually 100% success rate, in the case of successfully opening the garage door when all other criteria were met. The results of the range test can be seen in the table below. Our error came from two main sources: the tool we used to measure and the fact that we cannot move through walls to get the ideal point A to B distance.
Due to certain limitations, a few specifications were unmet or still left to do, with the first one being enable backgrounding functionality. Due to the software complexity and lack of experience building iPhone applications, not all of the promised specifications were implemented. This includes this functionality to operate and wake the from background state. This specification is vital to the design as it completes the entire automated operation of the system. With more time to restructure the application software, this specification could be met. Next we have enable user verification. The functionality to verify whether a user is valid or not was not implemented. This can be implemented by a method such as matching a hash string to the device's unique MAC address. Due to time constraints, this functionality was also not met. Finally, we have follow flowchart design as intended. Towards the end of the development process, a few aspects of the design had to be altered. This pertains to how Bluetooth packets were delivered. This involves building custom services on the microcontroller in order to carry out the desired functionality. Due to constraints, this functionality was still achieved but in a different manner. This was achieved by moving the workflow to the application side of the software instead.
Here is the bill of materials that we used for our project. The PSOC 6 creator module was $20, and then we had our DC barrel jack adapter, our relay, and our 2N7000 MOSFET. These were the cheaper of the components used in our project. And then we had the universal AC-DC power supply, which was $13, which brought the total to right around $40 at $39.70. For our budget, our original goal was to be less than $50. With an expensive microcontroller and an expensive wall adapter, this brought our total very close to that $50 goal. If we brought GarageAuto into production, the overall cost would decrease because ideally we would use a different microcontroller and a less expensive wall adapter